Thank you very much. Good afternoon, everyone. Thanks for coming to my talk. Does the sound levels good? Just check. Cool. Okay, so as introduced, the purpose of this talk is to discuss what happens when you join an AD domain and a UNIX network together. So by way of an introduction, I'm going to do a TLDR, I'll explain who I am, I'm going to give a plan for the talk, and then we'll break into the actual technical detail. So the TLDR, this is research in progress. It's about a year in now, but I've still got a fair amount to do. I keep on finding new vendors, I keep on finding new attack surfaces. I'm still quite enjoying it. It's not about AD, although clearly AD plays a part in it. This is about what the attack surface of an AD joined UNIX estate looks like. This is how, if you get a shell prompt on a UNIX system on an enterprise network, you might find that you've actually got more credentials than you thought you had. So who am I? So I'm Tim. I have a background working for financial services organisations, and for the last 15 years or so, I've been working for Portcullis and now Cisco. Used to work with Graham. I've spoken at Securi-Tay before. I spent about 3 years ago looking at Red Team and DevOps. But yeah, I like bug hunting. I'm offensive by nature. That said, the financial services stuff was an operational role, looking at security from a defensive perspective, and probably for the last 18 months or so, I've been focusing back on the defensive side. So one of the key takeaways from this talk, if you take anything away, is that there are mitigations, there are things you should be doing to defend your UNIX estate better, and certainly some of the stuff that's been published off the back of this so far is very much geared at how you protect yourself, not just how you attack. So the plan for this talk, I'm going to give a little bit of background for those of you that perhaps haven't had any familiarity with what AD on Unix might look like. I'm going to run through the theory. I'm going to look at some possible attack chains, broadly speaking modelled off similar attack chains on Windows AD joint systems. We're going to break into some mitigations and recommendations. Going to talk a little bit about vendor response, because the vendor response has been interesting. And finally, there's been some conclusions. Probably a slight change from the last time I presented this. The bonus material on this occasion will be more detailed look at recommendations and mitigations. I switched it up a little bit for this audience. I'm going to spend a little bit more time looking at how I came to find these vulnerabilities, how I came to find these weaknesses, the tools, tactics and procedures for doing the research, and a little bit less time on what you should do as a vendor or as an enterprise. Because I think in an audience like this, there's probably more interested in breaking things than necessarily in defending. That said, when you go into the real world, I think you probably need to think about both. So the background. When I started doing operational security on the Unix estate 20 years ago, we were using Tivoli to essentially manage flat text files, etc., password, etc., shadow, etc., security password. The normal files you'd expect to find on a Unix system, we're essentially managing those via rather horrific enterprise applications written by the likes of IBM, which are essentially modifying those files in real time as you made requests from your graphical user interface as an administrator. These days, a lot more systems are looking to be AD joined. I had a conversation just this week with a company I'm working with at the moment, UK-wide retailer, building out their cloud infrastructure in Azure, and they wanted to say, what do we do about the Unix boxes we're going to have in this cloud environment? How do we manage the identity on them? And we started talking about, AD is the right way to go in the sense you have centralized management, you can apply the policies, all that good stuff, but these are the things you need to think about because maybe your Unix administrators won't be familiar with the attack surfaces that they're inheriting. So that's a little bit about the why. Let's look at a specific implementation. So, Vintella, this is one we see an awful lot. We see it in our customers, and indeed, it's probably not something that's called out directly on the slides, but it's actually something that Cisco uses internally for our network. So it's an obvious place to start, but there are other implementations. So why does it all matter? Look at it from a commercial standpoint. We're expected to push the IT envelope. We're expected to be able to tell our customers how to secure their networks. We're expected to be able to secure our own networks. From the perspective of the team I operate in, that's even more true because we're directly out there consulting to customers. I mentioned the customer that's doing the Azure stuff. Yeah, if I can't give sensible answers to those questions when the customer comes to me directly, it's not much use. And then you look at the bigger picture, we protect an awful lot of networks. So, yeah, I like bugs that scale. This is a bug that scales, or it's a weakness that scales, to be entirely fair to the vendors concerned. So, I mentioned I was going to talk a little bit more about how we went looking at this. The approach was pretty iterative. I started off by building out an environment that I could test against, that I could research, that I could evaluate. Specifically, I started out with Vintel. I also implemented an equivalent environment using Red Hat's open source AD integration solution and a couple of others. But so I started off by building it out. Then I started to think about what the threat model looked like, because by that point I had some understanding of what was actually going on to systems. Then I started looking at what that meant as implications to those systems, and what were the attack surfaces that were changed by putting it on. Reviewed some of the configuration files around it. Then landed on the idea that perhaps I needed to fuzz some of those components. The open source implementations are great, but certainly the closed source implementations, you're not going to get very far merely looking at it from a file perspective and looking at it from a configuration perspective. Reverse engineering, because I'm talking about the fact that this is something that's probably fairly similar to the weaknesses you'll find in Windows. The cryptographic side of things was definitely something that needed to reverse engineer. Development, more fuzzing, you can see the pattern that I went through. And as I say, it was iterative, but I wanted some output. So the theory of what we were actually doing, or the theory of what I was actually doing, was about attacking this. So that's what Red Hat's implementation SSSD looks like on a typical Unix infrastructure, typical Linux infrastructure, because of course it's Red Hat. So you've essentially got some authentication, some identity, you've got some policies, and essentially it's not dissimilar from the model you'll find on Windows. Obviously, Active Directory is providing the DNS, it's also providing the LDAP, and it's obviously also providing the Kerberos. SSD, if you want an analogy, is performing a similar role to LSAS on a Windows system, and it's essentially talking backwards and forwards to the Active Directory, making requests to validate users, getting Kerberos information back, applying that to the user's profile on the system they've logged into, yada, yada, yada. You can see why the attack surface might be similar, but there are some differences. So what do the attack chains look like? Well, I said I installed it and I was going to do some threat modelling, so actually I went away and threat modelled it properly. Cisco have a threat modelling tool we use internally, but I also use Microsoft Stride methodology and Microsoft threat modelling tool to give myself something that I could possibly share with other people. And essentially, in the end, I ended up building out a big spreadsheet, a big spreadsheet, as I went through iteratively. And every time I found something with one vendor that I thought was kind of interesting, I'd make a note of it to make sure I went and looked at what other vendors had done with the same design problem. And the spreadsheet at some stage or other will be something I'd like to share, because I think as an approach, it's quite useful to show how you go about doing this. But I actually think there are other implementations I won't get a chance to look at, and it would be quite cool to see other implementations get a similar level of exposure. So, Vintella, I said I threat modelled it. That's from Cisco's threat modelling tool, and each of those components has a set of attributes that define the threat models, the attack surfaces, etc. that are exposed. But broadly speaking, just as on Windows, you have a user that comes in over the network. They cross a generic trust line boundary. In this case, SSH. In Windows, it will probably be RDP, SMB, something like that. And they log in. And in the case of Linux, you log in through a process that hosts a PAM library, SSH or equivalent. And he makes some library calls down into the PAM infrastructure. The PAM infrastructure, in the case of AD, in the case of, in this instance, Vintella, but also SSSD and the other implementations, will typically use a UNIX socket to call out to the host process for the integration. So Vintella uses FASD, SSS uses SSSD, others will use different process names, but yeah, you get the point. That Unix socket allows PAM to talk to it, and then of course that service component then does the integration piece back into AD. So in the case of an authentication request, it may make use of LDAP, it may make use of Kerberos. Cached credentials is an interesting one. So Windows has had a long and torrid history of cached credentials being a source of weakness. You compromise a bunch, you dump the credentials, you can use those credentials elsewhere. Absolutely the same with FASD, with SSSD and other implementations. In the case of Intel, there's a whole bunch of things on the file system which are quite interesting, including the SQLite database and a cache at the end of that SQLite database that contains credentials of interest. So that's broadly speaking what it looks like. And like I said, if you look at it systemically, most of those attack surfaces have analogies, whether it's Windows or Unix. Yeah, you can take the same approaches, and of course other vendors do exist. The reason it's interesting is because on Unix we're probably 15, 20 years behind the times. I say that as somebody that spent their entire life working on Unix and trying to secure it as a platform, but we are 20 years behind the times. UIDs and GIDs are pretty much the only form of security barrier that really exists. I know people like to say that SE Linux, RBAC and such have improved state of affairs, but how many systems you actually see in the real world that have them effectively configured and deployed? At the very best you're likely to see is you're likely to have an estate where they essentially warn you on policy breaches. It's very rare that you'll have them fully enforcing, because if you fully enforce, then you have a whole additional management overhead. Comparatively, Windows has restricted admin mode for RDP, it has LSA protection, it has protected user security groups, it has TPM. Windows 10 has even more, as LSA credential isolation. So Windows 10, the LSAS process, the equivalent of VASD, the equivalent of SSSD, is actually virtualized away in a separate instance of the OS. So you have a very finite set of API calls that you can leverage as a normal user to talk to LSAS to make an authentication request or to gain access to your token. You really are quite well limited. So the thought question was, what if I can get into Unix boxes? What can I do? And how do I determine whether I can attack any of the AD infrastructure by getting in? Isn't a huge amount of tooling out there. And in fact, I think it's fair to say there's no useful tooling out there, certainly from an offensive perspective. There's a few vulnerabilities that have been published for some of the implementations. SSSD in particular has a bit of a checkered history around its IPC, but there's not a huge amount out there. So the thought process went a little bit like this. People log into Unix boxes, they submit their AD credentials, and in some cases those boxes are quite interesting for their own sake. You talk about something like SAP. A SAP administrator has interesting privileges from a SAP perspective just by logging in, but there's a hell of a lot of other interesting privileges they may have on the network. Yeah, we're talking about a system that is used to, for example, host an application, and that application is developed in-house. Does that mean that I potentially have access to their Git repos, to their internal CI and CD infrastructure? Does it mean maybe I can get access to their mail and find out, that I can email one of their colleagues and get access to another system? It's a whole raft of different ways you can go, and most of the time people only really attack those on Windows at the moment. Opportunities to attack them from the Unix side are just as prevalent. So, some practical attacks. So, I've grouped them into four. So, SSSD, Vintela authentication services are around the AD integration present through both. LDAP and Kerberos, I've called out to them because whilst they can be seen as part of an AD integration solution, you will also see them in isolation. The canonical case is probably something like a web app. Enterprise puts a web app onto their infrastructure and they go, do you know what, we can't manage the user accounts individually for this system. We'll configure LDAP, and what does that mean? So, Red Hat's SSSD. It's open source. Potential attacks look like stealing hashes from the files, stealing hashes and plain text from memory. From a blue team perspective, it's relatively well hardened. I say that in the sense that from a compiler perspective, APIs are well used. There's a degree of compiler hardening around, for example, stack protection, etc. Notable point of interest, it does run as the root user. And as I alluded to, it has a bit of a patchy track record from an IPC standpoint. I don't think there's any public PACs around most of this, but that cached credentials one in the middle is actually relatively trivial to exploit. You could probably look at the patch that's available for that particular vulnerability and figure out how to trigger it. And whilst we'd all like to think that our Unix boxes are well patched and up to date, that's not always the case. I haven't written a public PAC for that. I have got a PAC that works, but it's just, as a point of principle, we ought to remember the fact that there is other work out there. So we digressed. I said I have an approach, and so that's what the approach looks like at the audit level. What I really wanted to do was understand what the attack surface was that was introduced by this software. So I was looking at the file locations, the file permissions, the contents of the files, processes, sockets, SDLC compliance. Go back to the SSSD slide I showed a couple of slides back. Always useful to know if vendors are compiling things in a safe fashion. Vintela, for example, they hadn't done a particularly good job of compiling that. It was pretty much compiled with stock GC settings from probably 20 years ago. Probably part of the reason I posit for that is the fact that it's available for a lot wider set of Unixes than Red Hat. And so many of those settings don't necessarily have a direct equivalence when you look up. If you run it on HBX 10.2 or AX 6.1 and you're running it with the IBM compiler, you're probably not going to have that equivalence of feature sets. So probably the view was they wanted something that would compile everywhere, didn't do too much work around improving the makefile for Linux, and so you end up with a situation where you're as good as the worst case. I also wanted to review what it looked like. When I say review, I guess understand what the difference was between what it was installed like and what it could look like. So that meant looking at the man page, looking at the configurations, looking at the logs. Tuning the logs to the maximum really helped in the case of Vintela, as an example. It didn't help from a security standpoint in the sense that it didn't make the product any more secure, but what it did mean is I had full access to all of the IPC traffic that was going over that Unix socket. Essentially, when you turned up logging to maximum, you got full hex dumps and everything. That was great when I started to build my fuzzer cases because it has had real-world, valid protocol implementation that I could work from. So that's the kind of artifacts you'll find in SSSD, and they range from cached hashes through Kerberos tickets right down to configuration files that contain potentially useful information. The bits that are in italic you can't get to unless you're the root user. It's a fairly common point of misconception because that's no different from Windows. You can't accrue other people's Kerberos tickets or accrue other people's password hashes on a Windows system without getting administrated. But let's remember, the purpose of this research wasn't to attack the Unix system that I had access to. It was to figure out how that Unix system became a toehold onto the wider network. So the point is, if you get root on a single development instance of SAP, does that mean you've actually got a whole stack of privileges that are associated with other systems on the network? And probably the answer is yes. Contrasting, as I said, Vintela is proprietary and multi-platform. Again, you can get hashes. Again, you can steal plain text from memory, and again, you can mess with the IPC. The IPC is more robust in the sense that there's no public vulnerabilities available for it. However, some of the research that I did indicated that there were probably exploitable conditions in the implementation. And when I say probably, I've worked with the vendor. The vendor has seen my fuzz code. My fuzz code is public. I'm not suggesting that there are free vulnerabilities out there, but whether the vendor has chosen to run my fuzz test cases through their entire infrastructure repeatedly to clean out all of the places that might be problems, that's ultimately their decision. They were pretty good in most other regards, so I'd expect they probably did. By comparison with SSSD, it runs as the daemon user, but it doesn't drop UID 0. That means if you get code execution, you would potentially have the ability to pivot back to the root user. So the use case would be there. I managed to do something terrible via IPC. I can still potentially get that to root. And as I said, because it runs on lots of platforms, it doesn't have the same depth of hardening, and of course it doesn't have any direct integration with SE Linux. Vintela have fixed that last point in the sense that they've provided an SE Linux policy that's appropriate for it. The entertaining bit is it's in GitHub in some of the personal repo that works for the company, and so therefore you're unlikely to find it without actually asking them and telling them that they don't have one. So, attack surface there, essentially where I was looking when I was doing the auditing. So again, we've got some cache credentials. Again, we've got some metadata and some configuration. Again, we've got an IPC. That IP is kind of quite interesting because it is exposed to normal users. There's a level of security control that's applied to it in the sense that essentially when you connect to it, you pass in a file descriptor. The other end validates the UID and GID of the process that owns the file descriptor and will selectively allow operations at the IP, say at C level, depending on the UID and GID of the connected user. That looks pretty effective in a sense that it reduced the attack surface to a non-privileged user, but there were certainly functions that were exposed that would be of interest that you didn't need to have privileges to access. And then, of course, we have the Kerberos tickets. Just by way of example, do everyone know what I mean by Kerberos tickets? Because I'm pretty sure you know what cached hash is, but I'll bet Kerberos tickets maybe not. Anyone not know what Kerberos tickets are? Okay, so Kerberos tickets are a way of essentially binding access to one system to an identity such that when you try and access subsequent systems from that first system, you don't have to go through a full round trip of authentication. You essentially end up with a cookie essentially that says the AD infrastructure has validated the identity of this user. Please continue to trust this user in this fashion. So being able to steal them from one user by gaining root privileges means that potentially you can jump from system to system relatively easily. So that's Vintela. LDAP. Again, we can steal credentials from memory. That shouldn't really be news to anyone, but it sometimes is. The middle point's kind of quite entertaining. The number of times you'll see web applications that have SSL on the administrative interface, on the user interface for accessing them, and then you'll go and look at the configuration that's used to do the authentication checks, and you'll find that it's not SSL all the way through. So if you were to sit on the outbound side of whatever the web server is, there's a reasonable chance you might cache those credentials going across the wire in a reusable form. That's the best way to describe it. And again, as with every application, where there's the opportunity for injection, you will find injection. And essentially, at the fundamental level, Kerberos isn't unique to Active Directory. So in a broader sense of the word, you may well find Kerberos takers in places you're not expecting to find them if you look for them. So what does Mimikatz actually do? As I said, you need to be privileged to use it. And as I said, these attacks are pretty well known in the Windows world. But from my perspective, I want to see whether I can do the same thing on Unix. And hashes, plain text, and tickets all seem pretty appealing. If I can get any of those three things, then I can probably do things that were intended. So hashes. If you try and run Mimikatz on a typical modern Windows box, you're likely to get caught by MDR. You're likely to get caught by AV. You're likely to be caught in some fashion or other. And indeed, you're introducing a new binary to the system in order to do it. In the case of Unix, the hashes, their files, the tickets, their files. But in this particular instance, the hashes is what I was interested in. So you're able to take the hashes, take them offline, crack them to your heart's content, and potentially reuse them anyway. But that's not quite as easy as it might seem. We're probably going to have to do a little bit of reversing. So talking about being iterative, at this point in time I was now starting to realise that I needed to pull apart some of the binaries that I was looking at. FASD, I wanted to know what it was doing below the surface with the cache credentials. They were a SQL-like database, I knew that, but you look at the table and you're going, well, that's not a plain text password, what is it? It's not an NTLM password, what is it? So there was a little bit of reversing to do there. Finding the functions, ltrace and strace. If you're not somebody that's intimately comfortable delving around in GDB, IDA, Hopper, whatever, ltrace and strace are a really good place to start. So strace will essentially give you system call level visibility of what a process is doing. ltrace does the same, but at the library level. So the way to think about it is ltrace is essentially your glibc, your individual libraries that come with an application. strace is what the kernel is doing in response to those library calls that you make. And ultimately, if you want to look at it from the perspective of how do I get into this easily, Hopper's a great place to start. IDA is obviously the reference point, NSA releases notwithstanding, but Hopper is pretty cheap, accessible, and functional. Certainly for the major platforms, iOS, OS X, Windows, Linux, you're going to be able to get a whole heap of the way with just Hopper. So perhaps have a look at that. And for me, I used to be one of those guys that would do my reversing by obj dumping a binary, essentially having a text file and then essentially annotating the text file. The fact that Binary Ninja has managed to persuade me that that's something that's a better way to do it, I think is telling. But essentially, Binary Ninja is similar to Hopper in the sense that it's relatively cheap to get, and it's a great tool from a reversing perspective. The difference between the two is Hopper is intended to be runtime, and Binary Ninja is meant to be more for static analysis. So anyway, breaking the hashes. SSSD is as simple as that. So if you look in the top left corner, right hand corner, depending on where you're looking at, you've got a database. That format of the database is the same as Sanders. It's essentially a standard implementation of authentication credentials that's used by a bunch of different open source tools, SSD and Sanders being two. But essentially you can dump them out. You see that it's a $6 type hash, so that's SHA-512. TDB dump will quite happily allow you to pull them out in a format that you can get the hashes. John the Ripper knows about that format. It's all relatively easy, assuming that you've got all the passwords in there, or you've got a good dictionary for the customer you're going after. They're simple as that. Vintella was a bit more difficult. So I mentioned it had a SQLite database, and I said that there was some bespoke caching algorithms. The good news is when I started to dive into the libraries, into the binaries, it did have its symbols. Going back to this point about them not perhaps being quite so proactive in terms of defending their intellectual property and defending their attack surface, we had symbols, which meant that I could start to figure out what the bespoke hashing algorithms look like. The legacy one, I never found it in the wild, so I haven't done a huge amount of it. But SHA-256 or SHA-1, depends whether you believe the name of the table or whether you believe the implementation. It is SHA-256. It's possible to reverse that relatively easily, and in fact we've done that. We've made the code available to do that, both the John the Ripper stuff, but also the stuff to do the extraction. And in terms of timelines, it didn't take a huge amount of time, pretty much a day. So what does it look like? So that's more or less the implementation that's used for caching hashes for Vintella. And it's essentially a case of a hash, a UUID, a hyphen, the password, and then essentially you SHA that, and then you base 64 it, and then you shove it into the SQLite database. Interestingly, that potentially goes in both directions. How much use you might find in that depends on whether you can find other ways of getting the data into the database tables. Obviously, the standard way is to log in as a given user. But if, for example, you were to find a way through the IPC layer to inject queries, hypothetically, then maybe you could write the hashes in the opposite direction, and maybe you can progress that way. So that's what Binary Ninjas gave me the ability to annotate, I guess is probably the best way to describe it. So yeah, that's me essentially annotating assembly using Binary Ninja. You'll see that essentially I've got the full set of function calls and the parameter values that are being passed in next to each of the assembly call instructions. So that gave me an understanding of what was actually happening. But it's not a standard implementation, so I had to go away and I had to figure out how to get John the Ripper to crack it. Those rules are now publicly available and will go to John the Ripper. One of the things that I'm going to point to at the end of this deck is a good write-up of how you start to write those rules, because they're not necessarily as transparent as one might hope. I don't necessarily know that I would have been able to guess how to write that from the start. Fortunately, there's some good blog posts out there, and Solar Designer, if you get to talk to me, is pretty helpful too. But essentially, in this particular instance, we've got a bit at the top that essentially says we're defining a new type of new dynamic type of rule. We've called it 1602 because 1601 already existed. There's an expression. That's essentially my way of telling anyone that's calling it which function definition 1602 actually is. It's essentially there for usability rather than because it adds any programmatic value to the definition. And then essentially you have the definition itself. So you have MGF input 32 bytes, which is a flag. You then have another flag, which is the username. You have the salted piece, and then you have the flat buffers. That essentially says this is how I'm expecting to construct hash or the plain text value from which hashes are built. I then define a couple of constants. That's because that's part of the plain text value. There's a hash and there's a hyphen in there. And I say that the sum length is 36. Then, on the right-hand side, you essentially have the function calls that you asked John the Ripper to perform when it's taking a plain text value either from its dictionary or from its brute force implementation and apply those in order. So you see it starts off by applying the sum being the UID in this instance. Then you apply the plain text value, that's the key. And then you do the final SHA-256 crypt operation. And then there's a test case at the bottom, and that's simply so that a maintainer of John the Ripper go-forwards or a John the Ripper rule set go-forwards can validate that what the rule set says it does is what it actually still does. So they change the implementation of the SHA-256 crypt final operation. We want to know that this is still functioning correctly. So, Vintella was a bit more interesting in terms of plain text memory. SSSD, I didn't find anything particularly mind-blowing. But in the case of Vintella, under certain circumstances, you do end up with plain text values being left in memory for a long period of time. So essentially, if you could dump the VASD process, you get the password that was used to log in, or the passwords that were used to log in. Turns out that's because essentially the memory management routine runs as a separate thread, and it only runs under certain conditions. It's not essentially a continuously running thread. It happens when Vintella thinks that a user has successfully logged in, because it holds that password so that if you need to do a password reset because your domain account has a password that's expired, it's still used. Rather than ask you for the password again, it will go and do that initial piece for you. Consequently, we can get plain text values out, and it's dead easy. Gcall, GDB, string, job done. So that's why it's worth knowing, because if we don't look at those kinds of things, we'll miss low-hanging fruit, and that really is low-hanging fruit as far as I'm concerned. So, tickets. Tickets are fun. So if you get a ticket, that's essentially one of those files that lives under TMP. You can probably assert the owner of that ticket's identity against other parts of the network. Variety of ways to do that. The most reliable I found was SMB client and RPC client, so that's the SAML implementation. Go figure. They've been working with AD infrastructure for God knows how long. I think they actually performed the first viable attacks against some of the cryptographic weaknesses in Active Directory and in NTLM. Mimikatz works quite nicely. If you can take the ticket file off the UNIX system and copy it onto your Windows system, you can load it into Mimikatz, process it, and do useful things with it that way. SSH is kind of a real bugbear. So in principle, if you've got a Kerberos ticket, you can log into other Unix systems too using the Kerberos ticket. The problem is most of the time SSH isn't actually configured to use Kerberos tickets at all, which actually begs the question: why are you actually issuing Kerberos tickets, or why are you asking the Active Directory KDC to issue Kerberos tickets to begin with? Because you're never going to make use of once you're logged into the Unix box. The only time you would ever use them is if you were either connected to other boxes that supported over SSH, and the configuration is rarely switched on, or if you were connected back to NTLM Kerberos-enabled web applications. Well, the chances of you opening up a browser on your SAP production environment is probably fairly slim. Wireshark's kind of quite fun. So if you get the tickets and you've got the ability to view the traffic from Wireshark, which obviously if you're root on a system you might do, you can potentially start decrypting traffic that might be of interest to you. You might be able to decrypt traffic from other systems too. And of course that gives you more options in terms of where you can go attack-wise. X3RDP, depending on which document you read, RDP supports Kerberos, so it doesn't. Some suggest it's essentially just for identification of the system to which you're connected, but there is also some suggestion that Kerberos is supported I've never got it working. It's one of those things I'd like to spend more time on. So, Kerberos tickets, that's how easy it is to change identity if you get one of those files. So in the left-hand side, I've logged on as the administrator, and I've got a ticket for administrator at thirdparty.example.org, and great. Right-hand side, I've got root. Maybe that's through a vulnerability in an application. Maybe that's because I had sudo access as a normal user. Whatever. I've got access. I've got root. So I've copied the administrator's ticket. I've then become another non-privileged user. So in this case, user at LNX. And then I've set the appropriate variable to the ticket that I've just stolen. And now when I run klist, I'm essentially administrator. So that means that anywhere that ticket, that KDC, that AD implementation trusts the identity that's being asserted through Kerberos, now thinks I'm potentially administrator, up until the moment that ticket expires. So the purpose of Mimikatz is basically to weaponise this and make it an effective tool from an attacker's perspective. What it essentially does is harvest those different credential sources. So it harvests the hashes, it harvests the tickets, it harvests the plain text memory, and essentially means that you end up with something that might take 15-20 minutes to do, otherwise taking 2 or 3 minutes, and potentially being something you could do even if you don't have a full shell connection to the system you attack. But I didn't really want to stop there, because that only works if you've got a shell of some description. It also only works if you can get to the point where you can set your shell script to an executable and get it to run. Lots of times when we break into UNIX systems, or systems in general, we actually end up with probably a metasploit, the turbulence type shell. So I figured, let's go and write some post-exploitations modules for metasploit. Then I thought, I've reverse engineered the protocols, I've reverse engineered the hashes. Would be good to make those publicly available so that if people dump the hashes, they know how to use them. So the John the Ripper rules are also available. Then I thought, do you know what? I'm not just going to put this out on its own. I'm going to give UNIX guys a chance to defend themselves. So I wrote some Audit policies to help blue teams defend against this kind of thing, or even to detect if it's been really happening. And then I thought, well, I'm probably going to end up putting out the research notes and fuzzers, etc. And we are gradually getting there. So that's the repo today. And that's what it currently contains. A step on from that, the Metasploit framework stuff is going through the pull process to go into Metasploit proper. The big sticking point at the moment is that Metasploit wants to build a full AD environment so they can reliably test the modules I've written. And I kind of said, I've done my work. I've got other things I want to break. I don't really want to spend my time administering Metasploit's Active Directory estate. So they're busy building some test cases so that they can reliably test this, and then it will be a Metasploit mainline. Audit.rules, well, that's the Audit D stuff. It's probably useful to have a look at from a wider perspective. I've obviously written rules that are very specific to the types of attacks I'm performing here. But actually, if you administer a UNIX box and you know what your crown jewels on that UNIX box look like, learn how to write Audit D rules that monitor those functions. And the data in the tools directory, well, the tools directory actually contains some of the tools I've been working on. And we'll discuss that in a little bit. So what do mitigations look like? So, you've got generic hardening, you've got the restriction of UID 0, you don't really want people to reroute your systems. You can lock down ptrace, a number of different ways you can do that. You can protect the resources with SC Linux. You can apply additional orders so you can read the manual. I said there was some bonus material. Each of those has a slide of its own in the bonus section of the deck. But instead of that, let's move on to recommendations, and I'll show you why. So, recommendations. This is for developers as much as anything. Please harden your binaries. Permissions. Yeah. For the most part, the permissions on the stuff I was looking at was pretty good. But those IPC interfaces, do they really need every user to be able to have access to them? And do they necessarily need people to have access to everything that's exposed through them? Memory management. I talked about fuzzing and the fact that perhaps there are some places I thought there might be interesting work further to do. Make sure your memory management is shit hot if you're going to write C. And cryptography. The Vintella guys were really good, so they've already ripped out that hashing implementation that I reversed and replaced it with an off-the-shelf bcrypt solution. But if you're going to choose a solution to store sensitive information, use the right solution for the job. A straight hashing algorithm really isn't right in this day and age. A KDF or something like that is far more appropriate. So speaking of responses, that's what Vintella did. Ironically, by the time they sent me their IPC framework, I'd already figured out enough that I was quite happy making things do what I wanted them to do. But they actually shared their internal SDK, which I thought was pretty sweet. There's very few vendors out there that go that far in extending an olive branch where the security researcher comes and says, hey, I've got some problems with what you've been doing. They re-implemented the hashing algorithm for their caching infrastructure. They acknowledged the fact that plain text memory was a problem, and have been working on how they can clean that up in a neater fashion. Their view is essentially that the memory would only get cleared when it got freed, and they've acknowledged it. So under certain conditions that wasn't happening, so they're going to go back and figure out how they're going to do that. And they put in their SE Linux policies. I wonder how many vendors out there could even tell you they've got an SE Linux policy. I know I criticised them right at the very start for the fact it wasn't particularly easy to find, but hell, they've at least written one. Other vendors have been reasonable. When I wrote this deck before Christmas, they'd had relatively short timelines, 30, 40 days, so I didn't feel it was fair to mention them. Haven't actually heard very much from them since Christmas. So it may well be that I may be slightly more critical if I ever run this team again. But for the most part, they've acknowledged the problem. It's one as much, I think, of education as it is necessarily a problem of the implementations. As the people that are writing Vintella SSSD, ultimately you're beholden to the architecture that's given to you. I talked about the fact that Windows have made massive strides to harden their environment, to make it far harder for you to attack LSAS. Realistically, the only people that are going to be able to make those kinds of changes are the Linux kernel folks. And in fact, that was a direct conversation I had with one of the other vendors, was they were saying, well, actually, do you think we can do similar things to what they've done on Windows? I said, well, realistically, yes, if you could influence kernel design, not likely to happen, unfortunately. So, conclusions. What have we learned? What are the next steps? And thanks. And the next steps bit I think is kind of quite interesting, if you like to play along at home at least. So, what have we learned? If you get onto a UNIX box, there may be ways for you to get access to your Active Directory network. Passwords and hashes need to be protected wherever they're stored, not just in the places that people are most familiar with. Likewise, trust relationships. Just because a UNIX guy doesn't necessarily understand Active Directory doesn't make it any more forgiving when eventually that becomes a bullet breach. And probably at some stage or other will do. Yeah. I've seen ZOS boxes being used as points to pivot into networks. So it's not beyond the realms of possibility that a Linux box will be too. If you're going to use Active Directory, please read the manual. Please understand what you're switching on. The caching of hashes is a good example. Windows allows you to turn it off. We'll actually say that the vendors of SSSD and Vintella FASD, it's just not the default. Next steps, I kind of want to keep on kicking the IPC because I'm pretty sure there's some interesting bugs that will drop out of it. And I really do want to try and continue working with the vendors. I'd like to do some focus research on the group policy side of things, because it got mentioned at the very start and then I kind of zipped over it. If you're applying group policy to Unix boxes, you've got to be doing it through some level of orchestration. That orchestration is almost certainly going to be something that we should have some fun with. Improving the Meterpreter post-exploitation modules. That's a broader point. It's really shocking that Meterpreter doesn't have a good mechanism for dumping process memory on Linux, on Unix infrastructure. If you want a summer project, I don't know if Metasploit are doing their summer code this year, but if you want a summer project, if you want a holiday project, you want something to do in the evenings because you're bored, that would be a really sweet contribution to Metasploit. And as far as next steps, if you do fancy playing with Vintella or SSSD, I'm gradually starting to put out the code to enable you to do that. The UNIX socket side of things, there's a few tools that are publicly available and have been available for a while. UNIX socket scanner, SOCAT. But they didn't work particularly well for this. So you end up developing stuff. So for Vintella, there's a whole bunch of fuzzers that are sitting inside the GitHub repo. I would suggest that if you fancy bug hunting, they might be a good place to start. Broadly speaking, the approach I took was to dump out the raw IPC packets from IPC by enabling it in the login, and then use that to craft a corpus of messages, and then used a C script to essentially manipulate those messages. I don't know how many of you are familiar with Charlie Miller, but essentially his dumb fuzz routine, which is essentially for a random percentage of bytes, you change that byte by a particular operation. In my case, I think I went for XOR. And essentially you end up with packets that are largely compliant with the original specification, but have some minor tweaks. And then I just replayed the back and saw what crashed. And things did crash, and other things did happen. It was all very fun. So broader point perhaps, if you're going to fuzz stuff, turn off auditing really does help you figure out what's actually going on. If you can find a way of getting hex dumps for the protocols you're fuzzing, it's a great place to start, particularly if you're lazy. And Charlie Miller's fuzzing approach, AFL does a wonderful job, but you really don't need to do the level of machining that has been done in some cases to get good results. And that's some of the output from the development side of things. So those are if you wanted to get involved, those are the kind of things you want to start looking at. Thanks. Just a few of the people that helped with this research. Solo Designer is probably a good place to start, because without him, John the Ripper wouldn't even exist as a project. Many of those other people have done awesome things for our community. Vendors, because they always get a really, really bad rap. Vintella, the One Identity folks were fucking awesome. I wouldn't be able to talk about this without their support over the last year or so. Finally, some useful links. And I say finally, because I'm hoping you guys are going to have some awesome questions. Or you're not. I might get off scot-free. Sweet.